Hello and welcome. Today, we are going on a really cool journey of transformation. Seriously, we're going to take a simple block of ice and figure out exactly what it takes in terms of physics to turn it all the way into super hot steam. All right, let's dive right in. So let's just start with the big question. You toss a block of ice in a pot, you turn on the stove. What's really happening on a molecular level? How much energy does it actually take to push it from a solid to a liquid and then all the way to a gas? It's definitely more complex than you might think, but hey, we're going to break it all down. Okay, so the very first thing you've got to get is that there isn't just one thing happening here. There are two totally different jobs that the energy has to do. One job is making the substance hotter, and the other, completely different job, is to change its form. And for two different jobs, you're going to need two different tools. Think of it like this. The first kind of energy just makes the water molecules dance faster and faster and faster, and that's what we see as a temperature increase on a thermometer. But the second kind of energy, it doesn't speed them up at all. Nope. Instead, it works like a key, unlocking the actual bonds that hold all those molecules together. It lets them go from that rigid solid ice to a flowing liquid, or from a liquid to a gas just floating around. So let's check out our first tool. This is the equation we pull out of our physics toolkit anytime we see a thermometer's reading actually going up or down. This one is all about changing the temperature. And here it is, E equals mc delta T. This is called the specific heat equation, and it is our go-to for figuring out the energy needed to change something's temperature while it's staying in the same state. Let's break this down. E is the thermal energy we're adding, measured in joules. M is the mass in kilograms, pretty straightforward. Delta T is just the change in temperature. But C, the specific heat capacity, now that's the really interesting part. It's kind of like a personality trait for a substance. It tells you how much energy it takes to raise just 1 kilogram of it by 1 single degree Celsius. So, here's the crucial physics point. When you use this equation, E equals mc delta T, all that energy you're putting in is going into one thing: increasing the kinetic energy of the molecules. You're just making them wiggle and jiggle and move faster. You're not breaking any of the bonds between them. Not yet, anyway. Now, take a look at some of these values for C, the specific heat capacity. Check out water. Its value is a whopping 4,186 joules per kilogram per degree Celsius. Now compare that to something like copper, which is way down at 385. This means water needs over 10 times more energy to heat up than copper does. This super high specific heat is why oceans can absorb so much heat from the sun, and, why it feels like it takes forever to boil a pot of water for pasta. Okay, let's make this real with an example. Say we want to heat 2 kilograms of water from a cool 20 degrees up to its boiling point at 100 degrees. We just plug the numbers in. The mass is 2, we'll use a rounded value for C of 4,200, and the temperature change is 80 degrees. You multiply them all together, and bam, you get 672,000 joules. That is a lot of energy just to get the water hot. All right, let's move on to our second tool. This is the one we use for those really weird moments when you're pumping tons of heat into something, but the thermometer, it doesn't move one bit. This is our breaking the handcuffs tool, the one we use for a phase change. And the equation is just beautiful and simple. E equals m times L. This is the latent heat equation. So again, E is energy and m is mass. But L stands for specific latent heat. Now the word latent literally means hidden, and that's the perfect way to describe this. This is the hidden energy you have to pump in just to break those molecular bonds and change the state, all while the temperature stays completely, totally constant. This just nails the whole concept, right? Your ice is melting, it's obviously absorbing heat from the stove, but a thermometer sitting in that icy water is just gonna sit there reading 0 degrees Celsius until the very last sliver of ice is gone. All that energy is busy breaking bonds, not raising the temperature. And just like C, L is a specific property. But there are two main types you'll see. There's the latent heat of fusion, that's LF, which is for melting or freezing. And then there's the latent heat of vaporization, LV, for boiling or condensing. And just look at the difference for water. It takes 334,000 joules to melt a kilogram of ice, but it takes a staggering 2,260,000 joules to boil that same kilogram of water into steam. That massive amount of energy is exactly why a steam burn is so much worse than a burn from hot water. So let's go back to our 2 kilograms of ice at 0 degrees and calculate the energy to melt it. It's just mass times the latent heat of fusion, so 2 times 334,000, which gives us 668,000 joules. Get this, that's almost as much energy as it took to heat the water by 80 degrees, but in this case, the temperature didn't budge at all. Wild. All right, time for the main event. We have our 2 tools. Let's put them together and map out the entire journey, from a block of ice below freezing all the way up to steam that's above boiling. It's a 5-step process. This heating curve you're looking at, this is our roadmap. It's super important. Whenever you see the lines sloping upwards, that means the temperature is changing, and we use our first tool, E equals 𝑚𝑐Δ𝑇. But whenever you see a flat plateau, that means the state is changing at a constant temperature, and that's when we pull out our second tool, E equals ml.
So this breaks our entire journey into 5 clean stages. Step 1, heating the solid ice up to 0. That's a slope, so we use E equals 𝑚𝑐Δ𝑇. Step 2, melting the ice. That's our first plateau, so we use E equals ml. Step 3, heating the liquid water. Another slope, so we're back to E equals 𝑚𝑐Δ𝑇. Step 4, boiling the water into steam. That's the long plateau, so it's E equals ml again. And finally, step 5, heating up the steam itself. That's our last slope, so it's back to our old friend, E equals 𝑚𝑐Δ𝑇.
So let's look at a quick 2-step example right here. Let's say we want to take a small ice cube, maybe 35 grams, from 0 degrees solid to 5 degrees liquid. Well, step 1 is melting it. We use E equals ml, which takes 11,550 joules. Step 2 is heating that newly melted water from 0 to 5 degrees using E equals 𝑚𝑐Δ𝑇, which takes another 735 joules. The total energy, you just add the 2 steps together, 12,285 joules. That's it. Okay, let's wrap this all up with a really clear summary of your physics toolkit. And, of course, some pro tips to make sure you absolutely nail these problems every single time. Here it is, the absolute golden rule. Before you even write down a single number, ask yourself one question. In this part of the problem, is the temperature changing or is the state changing? If the temperature is changing, you use E equals 𝑚𝑐Δ𝑇. If the state is changing, you use E equals ml. That's it. They never happen at the same time. It really is that simple. And finally, let's avoid the easy mistakes. First, please always convert your grams to kilograms. The formulas demand it. Second, double-check that you're using the right L value, LF for melting, LV for boiling. Third, never ever try to use E equals 𝑚𝑐Δ𝑇 for a phase change, because the change in temperature is 0 and the formula just won't work. And last, for those multi-step journeys, don't forget to add up the energy from every single step to get your final answer.
So now you have all the tools to calculate the total energy needed for any phase change journey. But here's a final thought to chew on. Knowing the energy doesn't actually tell you how fast it's all going to happen. I mean, a tiny candle flame and a giant jet engine could both deliver the same amount of energy, just over very, very different timescales. That question, how quickly energy is delivered, well, that's a question of power. And that is a topic for another day.